So, hello everyone. My name is Sanjay, and I work for the traffic team here at LinkedIn. And today we are going to talk about custom service discovery and load balancing solution that we have implemented here at LinkedIn for our reverse proxy workflow. Uh, so, uh, First of all, I would like to mention that we are going to discuss about the client side of the service discovery framework, not from the server side. For example, like for any of the service discovery system, there are two aspects. Like one is basically how each of the services are going to make themselves discoverable, like how they are going to announce or register with some sort of registry. And the second aspect is how those clients are going to talk to those services and how they are going to discover those services. So we are going to focus more on the client side of things, like how, as a reverse proxy, we are discovering those downstream origin servers and how we are doing the service discovery and load balancing for them. The framework is called D2, and yes.
It's named after all of this.
Sorry?
It's named after all of this.
Yeah. So I already mentioned like it stands for dynamic discovery, and yeah, we'll deep dive in later, and we'll get to know how it relates to the name and how it goes forward. So the first thing that I'd like to mention is like it's already open source project, which is part of our RESTly framework, and you can go ahead and check out on the LinkedIn's GitHub page, which has all the code base, and it talks about in detail, and there is a detailed documentation around the server side of the things and the client side of things as well. So what D2 does is essentially very simple. Like it needs a unique identifier for each of the REST resources in LinkedIn, and this unique identifier we call it as D2 service name. And given a D2 service name, D2 client is able to resolve it to a fully qualified domain name, and thus the service discovery part is handled in the D2 client, and then further we'll talk about like how we do load balancing using that information. But till here, it's the service discovery.
Wait, do you resolve it to a FQDN or an IP address?
It will resolve to an FQDN, not an IP address yet. So we
it's in your slide.
Yeah, it's a like my.hostname.biz, right? So it's not an IP address. It's going to be a hostname actually. And this is a known issue that we want to tackle, and next we want to do an IP address because that again results into one DNS resolution, and we don't want to do it. But right now it works well in our ecosystem. We want to emphasize that as well because of a constraint that we do not have the dynamic allocation of IPs for the host name. Most of the time, the host name is simply associated with a single IP, so that works well for us in the given time. But in future, if we want to go to some sort of like Kubernetes and all those kind of DSCP-based systems, then we will have to think about this. The other aspect that I want to focus on is like the D2 is like not a service, but rather than it's a simple library which can be plugged into any of the ecosystem from any of the services. As a server or as a client can import this and use it for the service registration or service discovery for the downstream clients. That's why we have implementations in Java, or it needs to be a language dependent library, and we have to have implementation in various languages that we support here at LinkedIn. This uses Zookeeper as one of our critical components as our service registry store. We'll talk about more in detail why Zookeeper and how we are able to leverage various features of Zookeeper in order to achieve an optimal service discovery. So on a very high level, there are two responsibilities, like we already mentioned, service discovery, which has the goal of maintaining a registry of all the online hosts for each of the microservices that we are going to talk to. And for load balancing, the goal is basically to ensure load is distributed fairly across all the downstream hosts so that we achieve optimal performance for all our servers in the for the origins. So before we go forward and talk about more into details of why you use Zookeeper and service registry-based system, let's talk about like why not use simply DNS. That's out of the box solution and which works for most of the use cases in general. So first and the most important point is like LinkedIn has hundreds and or thousands of servers and which are spread across like thousands of microservices. And we also have auto scaling. We also have a very dynamic allocation and deallocation of the host for each of the downstream microservices that we are going to talk to. So in short, like it's a very dynamic environment in terms of like how the hosts are allocated and how the deployments work and how the service availability is looks like from a reverse proxy point of view. In those aspects, we noticed that DNS cache propagation and cache updates are kind of slow, and they're not able to catch up with the service discovery information and becomes less reliable. This information we already knew, and we tried to solve this by using DNS as a service rather than just as a cache. And we have built something called as DNS Disco internally, which is a service which does health checks for all this downstream hosts that we talk to. And this health check is done like for a fixed time interval. Uh, but then again, we run into an issue of like how many health checks we can do for all the downstream services and what should be the time interval for doing the health check. Let's say if the time interval is too big, then we again have a dark period where we don't know what's the state of the server. And given that LinkedIn's QPS for some of the microservices, the QPS is in order of like 10,000s, and I would say even if we lose like 5 seconds of traffic, that's not acceptable like in terms of service discovery. Uh, and second point is like DNS provides a very basic load balancing. Like it does not have a ability to incorporate some sort of like custom requirements where we want to try out different load balancing strategies. So DNS can mostly provide like round robin or some sort of like uh, weighted round robin we can do. If for that also we have to do some sort of improvement in our DNS. It's not like out of the box available. Uh, and third use case that came up uh, within LinkedIn was the load test. In order to meet our capacity needs and do capacity planning for all the downstream services, we need to do frequent load tests for each of the downstream services. And uh, DNS does not have any like out of box solution to do like targeted load test for a single host or a single service in terms of uh, capacity planning or kind of like in isolated manner. So to solve all these problems, we had tried to incorporate the solution in the D2 framework, and then that's what we're going to talk about. So, so this is how it looks like. Whatever we have discussed so far, there is something called D2, which is part of our ATS workflow, which reads some information from Zookeeper to do the service discovery and load balancing. And then there are services which are talking to Zookeeper in order to do the announcement. And they also use D2 frameworks, server side of things, and in order to register successfully with Zookeeper, our service registry store. So, yeah, at this point, if somebody has any questions, we'll take some questions. If not, then yeah, I'll hand it over to Shivam. He'll talk about like how these details are implemented and how it looks like from the data modeling point of view and various other features.
Hi, my name is Shivam. Now we are going to look at how Zookeeper is used for service discovery within T2. So, uh, like you said, we need faster updates than DNS, and Zookeeper architecture is very well suited for that purpose. So, Zookeeper architecture is like we have an ensemble of Zookeeper hosts, and all of them replicate the same data. So all the updates are propagated to all the Zookeeper hosts, and typically this happens within milliseconds. Um, so and ATS uses the D2 library, which creates persistent connection with one of the Zookeeper servers. So in that way, we are also guaranteed to receive very fast and quick updates. Um, and Zookeeper offers functionality which is very well suited for service discovery. So essentially, we are going to have different microservices which are going to register with Zookeeper and and say that we are available to take requests for this particular microservice, uh, and we want them to be registered with Zookeeper only until they are alive. So if, for example, there's a power failure, then we want that node to go down. I mean, we don't want a request to go to that server. So for that, Zookeeper offers a concept of ephemeral data. So ephemeral data is kind of owned by the host which creates it. So a particular origin server which has registered itself with Zookeeper. Um, uh, so it creates a node, and that node is only active until its connection with the Zookeeper server is active. So this helps us like do some active health checks, uh, and the node will simply be removed when the connection breaks. And uh, for better performance, we are going to be caching all the service registry data contained within Zookeeper, and we are going to store it within memory in ATS itself. Uh, and so whenever there's an update in this data, we need to update our cache as well. And Zookeeper provides a functionality of setting up watches. So this allows us to get notifications for any updates to the data. So on the right hand side of this slide, you'll see a diagram of the data model that we use to store the service registry data in Zookeeper. So Zookeeper is modeled on a file system. There are directories, as you can see in this diagram, and each directory can have data as well as further children. And so in this diagram, you can see there are two subdirectories in the root directory, services and data. So within services, we are going to store all the services which are there in LinkedIn. So as you can see, there are two services here, foo and bar. And within these two directories, there'll be nodes, which are these are the origin servers, which are able to serve requests for these microservices. So, and these nodes are going to be ephemeral data because we want them to be available only till they are online and they are healthy. And we are going to configure watches on the directories foo and bar so that if there is any host addition or deletion, we are notified and we can update our in-memory cache. And the data directory is basically used to store some configuration data for our load balancing for these two services.
I have a question.
Yeah.
So you said that when a server disconnect or a origin server disconnects, the node will go away, right? And then whoever's doing the watch on that service will go ahead and get. What happens if the server like completely just goes off, like power, and doesn't actually close down the socket connection? I don't remember how that works in Zookeeper.
Actually, in Zookeeper, there's like a health check which is going on always in the connection. So every 1 second, there's like a packet which is sent to the Zookeeper server indicating the health plan.
So there's like a 1 second window in there.
Yes. Yes.
So that's the concept of like this ephemeral nodes in Zookeeper. So that's what it means. Like it just sets up a very lightweight thread with the server, and it keeps on sending heartbeat events. So if the server becomes unavailable for whatever reason, the thread dies, and Zookeeper automatically removes this node from the directory structure. And since we have a watch from our ATS process, we get notified, oh, this node is removed, and we don't care about whatever the reason was for the removal. We'll just simply remove from our load balancing hash.
And sometimes it can actually happen that the thread which maintains the connection with Zookeeper, it stays active, but the application actually has become unresponsive. So in that case, it becomes like a zombie host, and we'll see how we deal with that situation, although it's very rare. And now we are going to see how D2 does load balancing. So D2 supports two modes of load balancing. One is random. In this, D2 will simply pick one of the hosts at random. And the other one is called degrader strategy. And this is based on the idea of doing passive health checking. So the idea is that since we are making calls to all the origin servers, we can track the responses that we are getting from those servers and use that information to figure out the health of that of those origin servers. Um, so, yeah, this is what we do here. We are going to look at parameters like latencies and the response codes, error rates to see what hosts are healthy. I mean, to basically try to figure out the health of the host. And like we already discussed, we don't need to do active health checks because those are done by Zookeeper itself. So integrator strategy, we use two kinds of health tracking. So one is at the cluster level. So we track the overall latency of all the requests to a particular cluster. A cluster is basically just a group of servers serving a particular microservice. And we see that if the latency exceeds a particular threshold, then it's likely that the load on that cluster itself is too high, and we can try to drop a few requests and see if it gets better then. And we also do host level health tracking. So for every origin server host, we are going to see what's the latency and error rates we are getting from that host. And based on that, we assign a weight to every host. And if we see that a host is not performing well, we are going to reduce the weight for that host. And host is basically the probability of selection of that host for every request. So the hosts which have the higher weight, they have a higher probability to get selected for a request. And now we are going to look at how we implemented D2 within ATS. So it is implemented as a plugin, and it's both a global plugin and a remap plugin. So it needs to be global because it has to make connections with Zookeeper. It has to maintain a cache of the service registry data and all those things. Uh, and uh, and it obviously it needs to remap the destination URL. Um, so that's why it's a remap plugin, and we can see it on the example on the left. There's a simple remap rule indicating how we use D2 plugin. So we are simply passing a parameter uh, with the service name to which we want to route the request, and D2 will kick in and remap the request to one of the hosts of this microservice. And as the fallback, you can see that we have a DNS URL here. Uh, this was our default implementation before we implemented D2. So now it's used as fallback. So in case if D2 is unable to route the request, then we fall back to our DNS discovery mechanism. So we implemented D2 plugin by using the C++ API, and it's a subclass of the remap plugin. And here we see how ATS interacts with D2 plugin in this sequence diagram. So when ATS boots up, I guess it creates a new instance of the D2 plugin for every remap line where it is being used with the appropriate parameters. And when the request comes in, D2 will try to remap the request, and it can return either of these three status codes that we see in the diagram. So a result did remap is when everything was successful and we were able to successfully route the request. We use result did remap stop when we want to drop the request. So we can set the error response and drop the request right there and ensure that no further ATS processing happens for that request. And result no remap is when D2 failed to route the request, but we can fall back to DNS. And D2 registers for the transaction close hook because we want to get data for that for the response we got from the origin server in order to uh, I mean it's a feedback for our load balancing algorithm that we discussed earlier. And now we are going to discuss some of the advanced features of D2. Like we discussed earlier, we want to do frequent load tests for all of our microservices, and this can be done by modifying the D2 weights for the hosts of the origin servers. So this is actually some configuration that is stored within Zookeeper itself. So uh, uh, someone can modify those weights and will consume those updates and start sending more requests to one of the hosts in order to do a load test on that host. And when we increase the traffic to one of the hosts, we also observe critical parameters like the CPU usage, memory usage, etc. We can also do A/B testing, and we can ramp new microservices. New REST endpoints uh, in D2 configuration itself. As you can see on the left, we have an example of ramping a new service that we created using our A/B testing mechanism. So we have we are using a test key uh, which will be used to ramp to a new service called feed new. So earlier we used feed microservice. Now we can, based on this test key, we can ramp the traffic slowly and carefully to the new service which has been created called feed new. We also have quarantine feature within D2.
Nathan, yeah.
I don't know.
Okay. So we also have quarantine feature. So like we discussed earlier that sometimes Zookeeper active health check is not working properly and we can have zombie hosts which are unresponsive, but they are still there within the service registry, although it's very rare, but it can happen. And so for that, we detect that if there are several consecutive failures of requests to a particular origin server host, then we put it into quarantine. And then we perform active health checks directly from ATS on those hosts. And once we see that they have recovered, we can put them out of quarantine. Uh, and uh, and another feature of D2 is that we periodically write the service registry data to flat files. So if we boot up and Zookeeper is unavailable for some reason, then we still want to boot up ATS because it's a very critical service for us. So we try to do it on a best effort basis then, and we load the data from the backup files in case Zookeeper is unavailable. So I guess Sanjay is going to take over from there.
Yeah. So this is how it looks like from very high level, like what we discussed so far. Just to give a brief walkthrough, like user request is received on ATS and ATS invokes the D2 plugin. D2 plugin has been talking to Zookeeper in some way to get the data, and it sends back ATS a particular remap to host name and host name port name information, and ATS talks to that origin server, responds back to the users, and at the same time, ATS registers that response of that origin server with D2 plugin, so that D2 plugin is aware of like what's happening with a particular origin server in the last few requests, so that it can do an optimal load balancing from here. Yeah. So what next? Like it seems like we have solved like the problem that we mentioned in the beginning. With D2, we are able to get faster updates because Zookeeper watches are kind of instantaneous. We have noticed that within 10 milliseconds, they are able to propagate information to all of the LM proxy nodes if there is any change in the service discovery data. For custom load balancing needs, Zookeeper is still able to hold some data information in that node. So that's how we are able to propagate D2 weights or any kind of load balancing different strategy from the server side that can be consumed by the client, and client can react according to those configurations. And third is basically like the zombie hosts and all that are not now handled using the quarantine feature in ATS. And since like we already mentioned, Shivam already mentioned, these are like very outlier cases where we do not expect a lot of hosts to go into that zombie mode. So we have capped this at ATS level. We cannot do health checks for all the downstream servers. That again will end up in the same problem. So, but still that happens and it prevents bad traffic to such zombie hosts. Now, what is happening now is like as our ATS fleet size is increasing, and this is a client-side load balancer, and each of the clients are seeing its own view of the service discovery and the load balancing data. It's kind of triggering a herd behavior where each of the ATS hosts are going to take the same kind of decision, and they might end up sending traffic to the same origin host without realizing that they might actually bombard that host and kind of overload it. So it eventually catches up, but then again, like we are running into this problem, and we are kind of analyzing whether this will scale up further or not. If we, let's say, increase the ATS fleet size by double, what will happen to the origin service? And other than that, the next problem that we are seeing is like since the algorithm, the load balancing algorithm, entirely depends on the feedback mechanism from the last few requests. So if there are some microservices in the downstream that we are talking to, which have very low QPS, then what ends up happening is like the degrader algorithm becomes very inefficient. Like it doesn't know like what's happening with the servers, and because of the low QPS, and it cannot take a good call in terms of like doing load balancing. So we are trying to solve this problem as well. And the other section that we are kind of exploring is what should be the load balancing and service discovery granularity. Right now, we are doing service discovery based on the REST resource level. Like for each of the REST resources, we are maintaining separate load balancing hash ring, and we are doing separate service discovery. Everything is happening separately. Error rates, latency, all those metadata are like handled and affects the load balancing strategy on that level. But now we have noticed that with the pace of growth of LinkedIn, like there are like thousands of microservices coming up, and it's not going to slow down. So do we really need load balancing on like resource level, or should we have on a microservice level? That's the kind of discussion that we are trying to have, and trying to solve this problem, and how it's going to affect, or kind of is it going to improve or degrade the existing D2 algorithms. Again, like this, due to the scale, we are also running into the performance constraints as well. We recently realized that some of the algorithms are actually taking a lot of CPU power in the ETS process, and kind of slowing down the whole overall ETS. So how do we solve that? That's also on our radar. And last one is like that we already mentioned that this is a library-based solution, and since it's a library, we are language dependent, and LinkedIn is adopting new languages like going forward, maybe Go or Python, whatnot. So we have to maintain, as an owner of D2, we have to maintain the different implementation in different languages, and that also has its own challenge, some language dependent constraints, and that's also a kind of concern that we are going to address in the future. So yeah, that's it from my side. And any questions? Yes.
Two questions. One, did you guys look at software load balancers? Like VRT or something like that?
Yeah, but those are, yeah, we have a combination of whips on which handles the load balancing on ATS layer, right? Like how to reach
Yeah,
ATS.
downstream.
But for downstream, so like I said, like we wanted those custom load balancing information that I'm not sure like if WIP is able to support, like for example, how to do custom load testing or how to do different load balancing strategies. Like if you want to have a sticky kind of load balancing or kind of some other relative load balancing strategy that we are recently exploring. So that part is, I'm
I
not
mean,
sure.
they do that. They're
Okay.
pretty efficient. The only thing is the quarantine that you guys, or the
The zombie.
bucket testing, maybe
Okay.
it's possible to do weighted bucket testing. The other thing is, what is the microservices running on that doesn't have their own load balancing strategy? Like it's not a Kubernetes that.
No, not yet, but we are in process of moving towards Kubernetes. So that will also kind of affect our algorithm, like how we do load balancing on the client side. But yeah, that's kind of in future. Right now, from the server side, they're not doing any particular load balancing. They're relying on the client side to handle that. That's by design. Like I mentioned, the D2 library has a server side aspect of it, like where the servers need to import that library and how they do registration with Zookeeper. They need to provide like this is how we want the load balancing to happen in our cluster. So that's why like they are not doing anything, but they're just like advertising that information to all the clients that they are going to talk to, and they need to honor that information. And assuming like everyone is on D2 and everyone is going to use the D2 client library as well. So that works well in the Linux ecosystem.
And what kind of KPIs are you guys seeing on this?
Like from our ATS, we are over 1 million KPIs.
No,
like
from one host, not the ATS.
from one ATS host,
Yeah,
yeah,
one
we
ATS.
are able to do I think 5,000 or so KPIs. Like
And
right
it's still
now.
managing the memory and.
Yes, yes. So yeah, like a quick story around that was like a couple of quarters back, we were not able to do more than 2,000 QPS with ATS, but that turned out to be the problem with the allocation and deallocation of the memories. So after solving that problem, we are now able to do more than 5,000. But still, I think like we can do better because the reverse proxy workflow is not supposed to be that heavy and probably can do much better. So we are looking forward.
So does Zookeeper have like any hardware redundancy to maintain the to reduce
Yes.
use?
Yes, right. Like Zookeeper is by design like it's supposed to have the consistency, and they have their own architecture which ensures that we will get the consistent data, and but availability is kind of compromised there. So that's why we have built that caching system that we discussed earlier, the flat files, where we store the last snapshot of the Zookeeper known data, and then if there is a Zookeeper availability issue, then at that time we can still serve some of the requests based on the last snapshot, and there's a very small percentage of traffic which can drop because of some bad host which did not get.
And this Zookeeper setup is within, like let's say your front end and your Zookeepers are all within the same colo. There's no cross colo. Is there cross colo traffic? Or?
No, not right now. I guess from Zookeeper side, like from ATS side, we do cross colo, but Zookeeper is I think co-located.
ATS to D2.
Yes.
It's all within a colo.
Yeah, like D2 is a plugin which is just a part of the ATS process. So yeah, it talks to Zookeeper within the same call.
But is the traffic possibly a different colo?
It can.
So Zookeeper tells you that the
go to some other colo. Yeah, so ATS can decide that and will call another ATS in the different colo and the request. So that will end up with increased latency. That's by design, but that needs to be taken care of for the server announcement side, like, and they need to ensure that how they want the behavior.
Okay.
Did you consider an approach where all the D2 instances on the host would just communicate with like IGMP or some other form of multicasting so that you wouldn't need Zookeeper?
I'm not sure if this was considered like to use a different protocol completely in order to do the announcement, but yeah, I guess like that will still have those constraints in order to build up the whole infra for that and how it will perform on these ends. Sure.
Yeah, just to add, I think now we are looking at those solutions because we are looking uh, because due to performance issues of Zookeeper itself, we think that Zookeeper might not scale for us. So we are looking at service mesh-based solutions and also the ones, the multicast things that you talked about. Those are still being evaluated.
When you said you had Zookeeper and you're using it for some kind of system performance, like you were telling it when a system was overloaded, I was unsure. Were you talking about were you using ATS specifically as a metrics, like so many connections, like you said 5,000, 2,000? Or are you using, well, like CPU, RAM? I don't know, right?
Yeah. So a good question. So we rely on basically latency and error rates on a very high level, like not exactly on CPU and other metrics. So the assumption here is like if the CPU and memory are bad, it will show up as a symptom of like increased latency or increased error rates in some form, and those will translate into bad feedback to be true for the particular host, and then address those feedbacks in the algorithm.
You make it like an assumed thing, like latency indicates
Exactly.
performance.
Something is bad, like performance is bad on that host, and it's overloaded or it's not performing well, or for whatever reason. We the conclusion is do not send more traffic to this and kind of observe for the next request, is it improving or not? If it is not improving, then further we will degrade it like as low as like 0.9 to stop.
So, thinking just from my perspective, then like how are you registering differing hosts? Like how do you know when you have latency, you have the value of latency, right? So one host obviously will perform better than another based on hardware and things like that, or so we hope.
Right.
Right. But if you still run into a connection count issue, right? So in theory, higher performing hardware should allow more connections because it would not affect latency like this, right?
Yeah, so for that, it's like from the server side, you are supposed to send a certain set of information, like this is the max connection count that I'm expecting for each of the server. This is the max latency that I'm expecting, which after which just consider this as that simple as. So connection count is considered in that sense, but from the degraded algorithms point of view, it kind of that's a cutoff. Like if it is like more than this connection, do not send this traffic. But for latency and error rates, like it's a gradual decrease. If the latency is increasing, just kind of gradually decrease the traffic and observe. Okay, that's it, I guess. Yeah.